Hello guys, what's up? I am Hriday and this is an introduction video to quantum mechanics. Now I am planning on to make a course of quantum mechanics which would be parallel to the standard course taught in universities. I would be following Griffith's book on quantum mechanics. Now these are some prerequisites that you must know. So first of all, limits. That is basically 11th, 12th standard limits you should have an idea of. Then calculus all the way up to partial derivatives. This means integration by parts, partial fractions, chain rule of differentiation. You should be familiar with all of these things. I will be uploading a couple of videos to give just a brief idea of these. Some basic classical mechanics, such as the concept of momentum, energy, and force, among other things. Then vector algebra. Basically, uh, an introductory course to vectors. You should know how to add, subtract vectors, what are the different properties of vectors, manipulation of vectors, then vector calculus. Now, out of this, only divergence is mostly needed, divergence and gradient, and maybe something little of a curl. The integration, as of you can say, half the course is not needed. Then some idea of electrodynamics, thermodynamics, and waves will be helpful, especially waves, because we will be studying the wave function after all, so you must have an idea of waves. Finally, probability and statistics are a must, because quantum mechanics is by its nature statistical, so you should know standard deviation, mean, mode, variance. In this video, I will be talking about some prerequisites of these two. So let's begin. So suppose we have this sample data. These are suppose the ages of student in a school. Now, in context of quantum mechanics, these three are the essential quantities: mean, standard deviation, and variance. The mean can simply be obtained by x bar, that means mean of quantity x, sigma xi by n. This is the formula of mean. So, after mean, the second thing is standard deviation. Standard deviation is basically a measure of how the values are deviating from the mean. Before standard deviation, let's look at variance. Now suppose we have to find how much these values deviate from the mean. We could do this, that we could sum the difference xi minus x. That could give us an estimate of how these are deviating from the mean value. However, there is an issue. About the mean, the values are equally distributed. In simple words, there are almost as many values which are greater than the mean as there are less. So this could result in 0, which is obviously not true. One thing we can do is we can take the mod of this and sum. However, it is very difficult to work with mods, as you cannot differentiate or integrate them very easily, and quantum mechanics is already very complex. So instead of this, we use the idea that we sum the square of deviation and divide it by total number of samples and call this our variance. Variance is denoted by sigma square, and standard deviation is simply root of this, square root of this. Now there are some simple techniques you can use to find these. Now the formula of variance can also be written as variance of a sample is minus. Now here we are supposing that j is our variable instead of x. Now you could write the same thing using x. This is basically the variance of j. So this angular notation you must be familiar if you have read the kinetic theory. This signifies mean. Okay, so basically the variance of any variable j is the mean of the square of observations minus the square of the mean of observations. This is a very fundamental theorem and is always applicable. You can prove it using some algebraic manipulations. So this idea we will be using in quantum mechanics, this definition of variance. Now it can also be defined as, this can also be defined as the mean of delta j squared. Delta j basically indicates the difference between ith observation and the mean of the sample. So this is some introductory probability and stats essential for quantum mechanics. Now before ending this video, I would like to give you a brief idea of what we will be studying by introducing the Schrödinger equation. Basically, Schrödinger equation in one dimension looks like this. Now this equation is equivalent to Newton's second law in classical mechanics, F equals to ma. This is iota, square root of minus 1. This is reduced Planck's constant, the partial derivative of wave function with respect to time. This is same Planck's constant, the mass of the particle. This time the double partial derivative of wave function with respect to the position or x coordinate since we are in 1D, plus the potential times the wave function. Now this is what Schrödinger equation means in simple words. Now the idea of partial derivative is very simple. Basically, if suppose you have a function of multiple variables, let's say f equals to x times y, then dou f, this is called dou, by dou x will be, we differentiate this function with respect to x, keeping other variables, in this case y, constant. So the answer will be y. Now this is Schrödinger equation, and the aim of quantum mechanics is to solve this equation so as to obtain the wave function for a particle. And wave function is usually a complex function. The square of mod of wave function gives us the probability of finding a particular particle in a particular area. Now first we are taking the mod of the wave function, which can be positive or negative, and then we are squaring it. This actually the integral with respect to dx gives the probability. So the aim of quantum mechanics is to do all of this. In further videos we will see how wave function relates to the probability of a particle. Then we would study it for some specific potentials, the infinite square well, finite square well, along with the harmonic oscillator. So this was the introductory video to quantum mechanics. Please like this video, share this video, subscribe this channel, and tell in comments what kind of videos would you like to see next. Thank you.